All right, in this video, we're going to look at a couple of examples from your worksheet H, so hopefully help you complete the rest of the packet. And so in this first one, it says a paddle boat water wheel with a 7-foot radius has 1 foot submerged in the water as shown and rotates counterclockwise at 5 revolutions per minute. A bug is sitting on the wheel at point B. You start your stopwatch, and 3 seconds later, the bug at point B is now at its greatest height above the water. You are to model a distance h of the bug from the surface of the water in terms of the number of seconds the stopwatch reads. All right, so there's the diagram to help us out. And again, it's rotating counterclockwise. So when it talks about it being at its highest point, that's going to be the highest point. Now let's use some of these pieces down here to help us navigate and figure out how to be able to create an equation, because that's what we want to do here. We want to ultimately create an equation and graph to model this scenario. So to start out with, let's start by finding the amplitude. The amplitude, again, is how high the point travels above the center of the wheel. So we can see here that from the center of the wheel to the top, that's going to be the same as the radius. And so so the amplitude here would be 7 feet. And remember, that's going to be for our graph, that's going to also represent our vertical stretch. Now the period is how long it would take to get from a point to get back to its original location. Now let's look back up here. It tells us something important here. It says it rotates counterclockwise at 5 revolutions per minute. So we want to figure out, well, how long is 1 revolution? So there's a couple ways we could do this. We could think about it logically and think, well, if it's 5 revolutions per minute, well, we could convert that to how many seconds would it take for 1 revolution. And one way to do that would be to use dimensional analysis. So remember, we have 5 revolutions in 1 minute, and I know that 1 minute is 60 seconds. So again, I'm trying to figure out how many seconds 1 revolution would be. So remember, these would cancel out. So now I have my revolutions per second. So I would just have 5 revolutions in 60 seconds, which I can reduce that to 1 revolution would take 12 seconds. So 1 revolution is 12 seconds. That's what we put down there. So that's the length of our period. And we're going to use that to figure out in a little bit what the horizontal stretch would be. All right, let's talk about the vertical shift. Now remember, this is what we call sinusoidal. It's going to be a graph based on our unit circle. So our unit circle, if we were to apply this to this scenario, we would use like the x-axis as a surface of the water. Well, we can see that it's been shifted from here to our scenario that the paddle wheel is only 1 foot submerged in the water. That means that there's 6 feet above the water to the center. So the vertical shift is going to be 6 feet. And the phase shift. Okay, so the phase shift, to determine the phase shift of the graph, you need to know a high point, a low point, or a middle point relating to the problem. Here we know a high point, so we will do a phase shift on the cosine graph. Remember, the cosine, think about the cosine graph starts at a high. So instead of starting at 0, 0, it starts at the point where x is 0, y would be 1. So in this case, the phase shift you can get from this sentence right here. So 3 seconds. So we notice the bug on the wheel at that point, and we start our stopwatch, and 3 seconds later, it's at the highest point. So that means that highest point, so for our cosine function, that highest point is going to start 3 seconds after we started our stopwatch. Okay, so think of it that way. It's going to be at its highest point 3 seconds after we started our stopwatch. So it's going to be a 3-second phase shift. All right, so we want to come up with an equation here. So we're going to use the cosine function because, again, we're using that high point. We could have used the sine function, but it's going to be a lot easier to deal with the cosine function for this one. All right, so let's see what we know. We know that there's going to be a vertical stretch Our amplitude is 7, so it's going to be a vertical stretch of 7. Now let's figure out what our horizontal stretch is going to be. Now remember, for our horizontal stretch, we can take the revolutions, or 1 period. So 1 period here is 12 seconds. We always take the period divided by 2 pi. And so when you do that, we would get 6 over pi. So when we go to plug that in, so if that's our horizontal stretch, would be 6 over pi. When we plug it in, remember we take the reciprocal of that, so that would be pi over 6. And then we would have a vertical shift, or our phase shift rather, is going to be 3 seconds later. So we're moving that 3 seconds to the right, so we would say x minus 3. And we're moving it, our vertical shift would be up 6. So that would be for, if we use the cosine function, that would be our equation. So it'd be, 7 times the cosine of pi over 6 times x minus 3 plus 6. And let's actually create a graph, and if we want to create a sine function, I can show you how to do that. So we know again that it started 3 seconds, or that it was at the high point 3 seconds after we started. So I'm just going to use a scale of 3 seconds here. Okay, so I'll just count by 3s there on the x-axis. And we know the highest point, let's go back to our graph up here. So that highest point, if the radius is 7, and if now the surface of the water represents our x-axis, so it's in the center of the wheel would be 6 feet above the water there, the water line. 7 plus 6 would be 13. So the highest point above the water would be 13 feet. So that means it's going to be, since we have a, it's going to be 1 foot, oops, I'm right, 1 foot below the surface of the water would be the lowest point. So we would go down to -1 there. And remember, we can put our little horizontal line that represents the surface of the water. So that represents the center of the wheel. That center of the wheel has been moved up 6 feet. So that's where that would be. That's not a negative, that's just my dashed line there. Now let's start plotting some actual points. So again, after 3 seconds, that bug is at its highest point, which we now know is going to be at 13 feet. And we know the period for this is 12 seconds. So if I count from here, if I count from our starting point there, if I count 12 seconds, so we would have 3, 6, 9, 12 would be here. So that would be at 15 seconds is when the bug would be, after 15 seconds is when the bug is going to be back up at the top of the wheel. And then we could just start putting in some things. So we know that this is based on our cosine function. So remember the cosine function, it would reach its lowest point halfway around the circle, or halfway between 0 and our ending point. We're going to reach our minimum, which in this case, it's going to be our lowest point. It's going to be 1 foot below the surface of the water. And again, I'm comparing our parent function. So these 2 points here would be halfway between our high and our low. So I'm just going to put points there. And this represents that cosine function that we just came up with an equation with a minute ago. All right, if I were to extend this, we could see then that we could also create a sine function like that. So if I want to create an equation based on that situation, we don't have a horizontal translation. We don't have a phase shift there. So everything else stays the same. Remember, if we're converting or comparing between sine and cosine functions, everything stays the same except for the phase shift, because we're still going to have the same horizontal stretch, we're still going to have the same vertical stretch, we're still going to have the same vertical translation. The only difference between sine and cosine is with the phase shift. And so in this situation, if I look at the sine function, there is no phase shift. So we could write it like this if you wanted to, but that's what your sine function would be. And then to answer this question, how far from the water is a point after 5.5 seconds? We can use either equation. It doesn't matter which one we use, but x would be our time. And so let's just use the sine function. So there's less to do there. So this will just be a matter of just plugging it on your calculator. Make sure your calculator is in radian mode. And then when you do that, you should get 7.8 feet. Or if I use the cosine function, I would get the same exact answer. So that's how you're going to do this question number 1 from that worksheet. Now let's look at question number 3 from your packet. This is a Ferris wheel problem, another common type of problem that we would see as far as application of what we just learned about in this chapter. So here it says a Ferris wheel 50 feet in diameter makes 1 revolution every 40 seconds. The center of the wheel is 30 feet above the ground, and we're going to label the diagram. So this time, as opposed, it's a very similar problem to the one that we just did in the previous example with number 1, but this time they don't give us any of the, they give us a diagram, but they don't give us any of the values. We have to put this to piece this together. So let's see what we know. We know that the diameter is 50 feet, and so that means the radius is 25 feet. Okay, so let's just keep that in mind. The radius is 25 feet. So we can use that to find a couple values here. So if they say the center of the wheel is 30 feet above the ground, that means from here to the ground, that's 30 feet. And if the radius of the circle is 25, that means that the distance between the bottom of the Ferris wheel and the ground is 5 feet. So the minimum height of the wheel would be 5 feet above the ground. So that's where we would get on the Ferris wheel. And so that means that the center of the wheel would be 30 feet above the ground. And the maximum height of the wheel, well, if the Ferris wheel is 50 feet, and then we have the height of the wheel is going to be 5 feet above the ground, maximum height of the wheel would be 55 feet. All right, I think that's all we're going to need to be able to create our, or get all the information that we need for our equation and graph. All right, so the amplitude. The amplitude is the distance from the center of the wheel to the top of the wheel. So it's always the case. And so in that case, it's going to be 25 feet. The period. What do they tell us in the story problem? It says that we have 1 revolution is 40 seconds. Okay, so the previous example, they said, I think we had like 5 revolutions. Well, here, and so we had to use dimensional analysis to figure out what 1 revolution would be. Well, we don't have to in this case. In this case, they tell us that 1 revolution is 40 seconds. So that's the length of our period, is 40 seconds. Now, when it talks about, well, what's our value for B here? That's referring to specifically in our equation. So remember, we talked about in class that to figure out what the horizontal stretch or compression would be, we just take the length of our period. We always divide it by 2 pi. So 20, so if we reduce that, we'd get 20 over pi. And so that would represent a horizontal stretch. So a horizontal stretch would be 20 over pi, but that means when we go to plug it into our equation, we take the reciprocal, and that's what this is saying. For B in our equation, it's what's reciprocal of that, so that would be pi over 20. All right, so let's look at what the vertical translation would be. Remember, again, our center would typically be, if we think about the unit circle, be here at 0, 0. Well, now that center has been moved up 30 feet. Okay, so the center is now 30 feet above the ground. So that represents a vertical translation of 30 feet. And the phase shift, again, depends on which equation we're going to use, so we'll get to that in just a minute. So let's sketch a graph here of what's going on. So we have the center of the wheel is going to be 30 feet above the ground. And the highest point of the wheel is 55 feet above the ground. And the lowest point of the wheel is 5 feet above the ground. Okay, with the x-axis represents the ground now. And that horizontal dashed line represents the center of the wheel. So we know that a person would get on 5 feet above the ground, so that's where they get on. And we know that the period is 40 seconds. So I'm just going to put a point down here, will represent 40 seconds. Oops. So that's how long it's going to take for that rider to be back at the starting point, because that's the length of the period, 40 seconds. One time around the circle will be 40 seconds. So let's break that up. Well, we know half of 40 would be 20 seconds, and I know half of 20 would be 10. So let's just use a scale of 10 here. So that's how we can figure out what the scale would be, by just understanding that idea of the unit circle and breaking it up into our 4 key pieces. All right, so now that means that it would reach the highest point after 20 seconds. And so now let's create our curve. Okay, so now we see that this looks very similar to a cosine function when it's flipped upside down. So that's actually what this first question is asking us, write a sinusoidal equation with a negative cosine function. Because when I look at that, remember the cosine function normally would look like that. Well, this is the cosine function flipped. So we're going to have a negative out in front to flip it. And the amplitude is 25 feet, so that's our vertical stretch is 25. Again, we're basing this on the cosine function. So remember, we already found out our value for b is pi over 20, and you need to look back at that for what we just did here. And now let's talk about our phase shift. So there is no phase shift for this one if we just leave it like this. So I'm just going to erase this. I'm just going to say pi over 20 times x, because comparing this one to the graph that we have, it hasn't been moved horizontally at all. But it has been moved up vertically, and that has been a distance of 30 feet. All right, now the only difference between these and the other 3 is going to be that phase shift. Okay, so I'm going to skip down and we're going to look at what would the cosine function be? What would be a positive sine function? So with that, you're going to look at that part of the graph. And so in that situation, everything stays the same, except for now we don't have to flip it, so it's not going to be negative, it's going to be positive. It's still going to have a horizontal stretch, and so we represent that as reciprocal, which would be pi over 20. But for the sine function, we can see that's been moved to the right 10 seconds. So x minus 10, but everything else stays the same. All right, I'm going to write down what the answers would be for the other 2, but I want you guys to figure out on your own how you would come up with those other answers. So this would be the positive cosine. All right, and this would be a negative sine function. So if we were to flip this upside down, there's actually a couple that we could use, but this is the one that I'm going to write down. Again, I want you to see if you can come up with those on your own. All right, so hopefully that will be enough to be able to help you be able to complete the rest of that worksheet.